Ishak, Rishad, can you just confirm you can hear me?
Yes, sir.
Yes, sir, we can hear you.
You know, I'm audible, right?
Yes, sir.
Yes.
Okay. So I had in the last class summarized this greedy algorithm framework for maximizing a submodular function subject to some constraint. Could be a cost constraint, could be a cardinality constraint. And this was a greedy algorithm. Either you can pick the element that maximizes the conditional gain, or look at something that looks at conditional gain per unit. How this? Let us start this again. Yes. Okay. Yeah. So either you maximize the conditional gain itself or conditional gain relative to unit cost. Okay, and I had left you with a homework problem. I said, well, there's another problem, which is a dual problem, which is about monotone submodular cover, where we say that the function, the submodular function I wanted to maximize, right, in the here, right? So let's use some color coding. So this is the fs that I wanted to maximize. This now goes into my constraint, fa greater than equal to q. And the cost that I had, well, let's say just simple cardinality, which was sitting here as a constraint, now becomes my objective function, but I want to minimize it. I want to have the smallest cardinality, smallest cost set, such that I have at least Q coverage, right? This would mean at least Q% coverage, or at least Q diversity and so on, right? So whatever, a combination of these two. Okay, so did anyone try implementing it? This is interesting. Even if you give some thought, it's okay. Anyways, this would have entailed the use of Submodlib, right? So the homework I had left you was okay, this for this objective, right? You can have a greedy algorithm where you start with an empty set that is cardinality 0. And while the coverage is not yet sufficient, while the diversity is not yet sufficient, keep growing the set, right? Based on that which helps F the most, right? So you're still looking at the same criteria, F. You're not changed to any other criteria, right? Same old criteria. Right, and its gain. Okay, this is so you're finding that S star which gives you the maximum value over A. I mean, you can put a minus A, but that doesn't matter because A is fixed. In that add. So now this, in theory, this greedy will return this A greedy size, which is at least, or which is smaller than equal to some 1 of log max overall elements S of singleton sets S of f of S into the size of the optimal A. Okay, so look at it. This is because it's a minimization problem here. Okay, so because you're dealing with a minimization problem here, therefore we have an inequal, less than equal to inequality. It's a guarantee one. It will not be worse than so much big, right? In the maximization, you're saying you'll at least achieve so much. You'll say at most the size will be so much, right? So you had to try the greedy algorithm, implemented in Submodlib for some choice of find the solution. Now implement the greedy algorithm on the dual problem. You understood the problem at least, right? What do you think would happen in general? So the theorem says something. What do you think the solutions will turn out to be for the primal and dual? Let's say for comparable Q, right? So imagine that here, let's say I targeted a Q value. For some value of Q. So I basically picked up Q from here and fed this Q here. Understand how I would solve it? And then I would see, okay, what's the size of the A? Not just size of A, I would also look at what are the elements of A. So when we say compare, you cannot really, I mean, you can compare sizes. More specifically, the contents of the two solutions. What is your guess? Do you think they will be very different, similar? Yes, anyone? So I'll talk about my experience here. Right? So this is something we investigated long back, 2016, PhD student Rajesh Kulkarni. And we were trying to do machine translation there. We've been always trying to do, human in the loop machine translation. And back then, deep learning wasn't as developed. So what we did was we said, let's think of summarizing patterns in a large corpus to be translated. So goal: extract patterns from a corpus so that by translating the patterns, we can assemble the translation of the corpus. In the pre-deep learning era, this is interesting, right? So like matrix factorization. I factorize matrix into U and V. Right? So I'm trying to now factorize this corpus into patterns. Now you can imagine what you would be interested in extracting. So this is a corpus, sentence ID 1. You can see this, right? Accomplia should not be used in patients with severe hepatic impairment. Acta pain is used in patients with diabetes. And then we had some lexicons. We had these sentences and we had some lexicons. So drug, Accomplia is a drug. Severe hepatic impairment is a disease. Diabetes is a disease. Okay. And then we also had noun phrases. Noun phrases are, all of you know what a noun phrase is, right? So they could consist of adjectives followed by nouns. Or the lady in the room, right? So it could also have preposition embedded. So you could have long noun phrases as well. So these were all different non-terminals. So think of all of these as different types of non-terminals. Okay. So my entire corpus is now represented in terms of terminals and non-terminals. So these are the terminals. Okay? Terminal, you know what is in grammar, there's a terminal and non-terminal, right? So these are, think of these as terminals. Terminal tokens. I mean, the non-terminals could also come from, something like parse trees, very complex parse trees. Examples. We actually listed all the non-terminals and terminals. P is a non-terminals. Sigma is a list of all terminals. And you could have production rules which give you the terminals in terms of the non-terminals. The same sentence now you can see this is at the bottom you have all these terminals. And the top you have the non-terminals. So now imagine that the entire corpus is represented like this. And now you can have patterns. So you can see the patterns here, which are in terms of terminals and non-terminals. So be used in patients with NP, patients with disease. These are all patterns, right? Now, patients with NP is a generalization because disease could be viewed as a noun phrase. You have generalized it. Okay, so based on this, now you can look at coverage. How are these patterns covering? So we're looking, I mean, as you would expect, a coverage function would be very intuitive. So here, cover H is looking at what are the tokens covered by each pattern. So 1, 3, 4 is a span. 1, 4, 5 is a span. Basically, these are the tokens covered. Right? Think of these. It could also be non-consecutive, need not be consecutive. 1, 3, and 4 are covered. So sometimes when you translate, you don't translate the same order. We kind of accounted for that as well. Anyways, I don't want to get lost in the problem specifics here, but this is the overall setting. Right, so our goal was as follows. So given all these, so I've abstracted. Okay, so I've abstracted all of these at the top. Our goal was that there is a cost function QC1H is modular, right? So this cost function could be, say, size, cardinality, and let's take the cardinality as a concrete example. Cardinality of the patterns. Okay, and then you have a QC2, which is the coverage function. I've been trying to tell you about how patterns cover, right? So again, example. Coverage function. Okay. So there are two problems. You can see the first problem is what we are all conversant with, argmax of the coverage such that the size of the set is constrained by C. Right? It's a monotone. Mostly they're making a monotone. Our cardinality constrained submodular max. Right? And the second problem we have, so here we are trying to maximize something. Right? Maximizing. Maximizing the coverage. The second problem we have is in terms of QC1, right, which is a dual submodular cover problem. So you want to cover some D, right? So I mean, you could think of this D like before, right? I remember I talked about how your Q could have been a solution to a primal problem, and Q is a constraint in the dual problem, right? So I'll similarly do something like this. So I could say that D is a solution. Let's say D was a solution to this. I plug it in here and see what happens. Or I could look at it the other way. I could put in my C here based on what the minimization. Okay. So now we did actual comparison. Let's look at kind of patterns we give. Is this problem setting clear? Okay. So first of all of you are convinced, hopefully, that there is diminishing returns. What we see here is diminishing returns. As more the patterns you pick, the less the marginal gain. So diminishing returns confirmed. I mean, if you do brute force enumeration, you will find this diminishing returns. So you can see that start flattening. And let's look at some of the patterns, right? So in patients with HIT type 2, so these are instances. So actually the pattern is in patients with category 1 or contains category 2 MG of category 3. And these are the counts. Okay? 568 instances of in patients with category 1 or 91 instances of contains category 2 milligrams of category 3. And all these are instances, right? So these are instances, or in this left-hand side, these are instances. And what we found, the solution sets are found to be almost the same. Right? So this is a non-trivial, it's not some toy problem, right? So it's a very complex problem. So if you put the same, the Qs are compatible, or the Cs and Ds are compatible, then you find that the solution sets are nearly the same. Nearly is actually pretty much, I would say, they were like the same. Okay. I'm not claiming that it'll always be the same, but in practice. So, is this clear? Interesting. Okay. So I hope you get enthusiasm to try it out yourselves for your problem setting. But let's now look at more complex constraints. So constraints are not necessarily always very simple. Right? So sometimes you want to place sensors, or imagine wanting to place projector. So you don't want to have two projectors in the same classroom, unless the classroom is very big. Right? But in some classrooms, you may not want projector because maybe it's a different kind of class. Maybe it's communication skills. You want to test people without projectors. So often we have a constraint, a constraint set, and you say, okay, I have a partition P1, I have a partition P5. P1 consists of 1A and 1B, 1A and 1B. Let's say sensors. So either you pick 1A or you pick 1B. You don't pick both. Likewise, you could have another constraint over 5A and 5B, or 3A and 3B, and so on. So 5, maybe cameras. I don't want to place cameras. So one camera here and one camera here probably will capture the same. But cameras in two different orientations would bring more value. So I know these constraints beforehand. I don't want that to be discovered unnecessarily. That's there. That's known. So these are constraints, and we want to ensure that with every partition Pi, there's exactly one, not more than one element. Okay? Basically saying that not more than one element needs to be picked from each partition. Where to install cameras and what you expect from the cameras are another constraint. So this is a different view. Right? So either P1 is looking in 1A or 1B, or P5 is looking in 5A or 5B. Now I'm going to give you again, go back to matrix. The moment you say Metroid, you think of matrices. But what is a Metroid? I say partition Metroid, but what itself is a Metroid, right? And let me illustrate this with matrices. So we have again seen you have matrix, you have a set of its columns. Okay, so think of this as C1, C2, C3, C4, right? C5. These are the 5 columns of this matrix. And now I'll relate to this the definition of Metroid based on this matrix. We say that a Metroid with an independent S. Notion of independence is very specific to the problem. But let's talk of independence for matrices. We all know what is independence, right? So if S is independent, let's say if C1, C3, C5 is independent, then is it not necessary that C1, C3, which is a subset of C1, C3, C5, must be independent? Yes? Is that not necessary? It implies, right? So implication is there in independence. Any subset of linearly independent columns will be linearly independent. So that is property 1. Okay, so let's look at property 2. This is 1. So now look at the second property, which is exchange property. If S and U are independent, okay, one independent set of columns, another independent set of columns. And let me take an example here again. Let's say C1, C3 is independent. Okay. And let's say C2 is also independent. I mean, any single column is going to be independent, right? So the size of S is greater than or equal to the size of U. But is U a subset of S? Huh? Need not be, right? So then what this second property says is that there must be some element E in S. So this E could be, say, C3. It need not be C3. It could be also C1. But there must be one element. There must be some element in S that can be added to U such that U union E is also independent, which means oh. So which means that something erase. So either C1, C2 or C3, C2, one of them must be independent. Okay, so this you can actually verify. This is intuitive, but might not be easy to prove. But for matrices, right? If I have a smaller set of columns which are linearly independent, a larger set of columns which are linearly independent, all we are saying is there should be one element I should be able to add some element from the larger set to the smaller set and still have independence. You can prove this using linear algebra, not very difficult. Okay. So this is my second. And the third is all maximally independent sets, which means if you add one more element to that set, it doesn't remain independent. So all such maximally independent sets must have the same size. I mean, in the case of matrices, that's called the rank, right? Because that's the third property. Okay, so I hope this is very clear. Now you can have a different notion of independence based on some partitions. That's what you're trying to show. So you can have different notions of independence, and that will give you different matrices. Uniform matroid is a simple matroid, which is basically saying cardinality constraint. It's kind of every element is uniformly belonging to that constraint set. Right? Each element has an equal chance. There's no prior, basically. Uniform prior. Think of it that way. Partition matroids, basically, S must contain at least one element from each group. It's a partition matroid. Okay, you can define the notion of independence for each of these. I will not go into those details. But you basically these partitions are creating the notion of independence. So maximal set. What would be a maximally independent set in the case of partition matroid? One from each of these partitions. That's what you're proposing, right? Or a graphic matroid is one where the S. So the notion of independence has been already defined here. Okay. Here we are saying in the case of uniform matroid, S is independent if S size is less than or equal to K. If S contains at most one element from each group, then again we call it S to be independent. Right? In the case of graphic matroids, S contains no cycles, then S is called independent. In terms of edge, so it's a set element. The elements are the edges here. Here the elements are the points. Right? In the case of graphic matroid, what would be the maximally independent set? Huh? A spanning tree. So independent sets would be basically trees. So trees as independent sets, spanning trees as maximally independent sets. Right? So likewise, you can now, for all of these, you can write them. Here, it's different. Defined that one element from each group is an independent set. So maximally independent is will consist of one element from each group. Right? Likewise, for uniform matroid, if you fill up the size, then basically a maximal element. Simple ideas. So what happens if you have such matroid constraints? So you can do monotone submodular maximization subject to matroid constraints using the simple greedy algorithm, where all you're looking for is feasibility. Very much like constraint optimization. You remember projection? The projection step in constraint optimization, the proximal gradient or projected gradient version, right, of generalized gradient. It would take a step and then project it back, right? So the idea is very similar. What we are doing is this, which I'm going to just explain. This is akin to projection step of generalized gradient descent. So what are you doing? You're saying I'll find the E that maximizes the gain, but only included if is feasible. I mean, it will not violate the matroid constraint. Add the most beneficial E greedily if it does not violate the matroid constraint. Okay, so that's how it's similar to general projection step. And Nemoser again showed that for monotone submodular functions, the function at the S greedy obtained using this projected gradient, projected greedy, is at least half of that of the optimal. Okay, simple idea. Any questions? Okay, so you'll basically add, look at this element. Right? So if you had already one AB, let's assume that your Si minus 1 already had 1B. Now, even if 1A is the one that gives you the maximum gain, you won't add 1A. Okay. Add the next best one. Sorry? That is why it's greater than or equal to half. I mean, half has not got to do with the fact that there are two elements here. So in general, for all kinds of matroid constraints, is the half. Certain constraints, cardinality constraints, you have a special case anyway, right? So there you can get 1 minus 1 over E. Okay, so now can we do what we did for, say, again, using Lagrange functions? We included constraints into the objective function. Unconstrained submodular maximization can we do using this same idea. So what have we done here? We are saying that the constraint has been absorbed here. So C is a constraint, but it's absorbed here, like Lagrange multipliers. Okay. So max of fx minus lambda cs. Now you can do unconstrained non-monotone submodular maximization on this. Okay. So moment you do this, obviously, you'll have to also look at whether the function is going to be monotone. So the function may not be monotone. In fact, this entire discussion is for unconstrained submodular maximization when you have a non-monotone and the function itself is non-monotone. So what can you do? Let's look at the non-monotone case on the right. So because it's not monotone, simply greedily adding might not sound the theoretically most sound idea because it's not monotone. It could have shrunk. So the idea here is interesting. You say, okay, I'm going to start with two sets. Okay, one is A and the other is B. Okay, B is the entire ground set to begin with. A is the empty set to begin with. In fact, let me move them side by side. One not one below the other. And what I'm going to do, let me use different colors. Yeah, let me change the colors. So this is going to be green, and this is going to be red. Okay, so it's in red. We have to be consistent with this part. So what I'm going to do is I'm going to consider removing elements from B. At the same time, adding elements to A. Parallelly, I'm going to say. That's why the word bidirectional has come up. So I'll do bidirectional search. So search on A as well as search on B. Okay, but there's a small probabilistic aspect. So what would you do? Would you add to A or remove from B? See, the idea is also to make sure that A is always a subset of B. Okay, such that at any point we maintain that A is always a subset of B. The goal is to kind of convert somewhere where A becomes the same as B, or find the best of A and B. Let's look at that, right? But what would we do? Instead of just deciding to add to A, I would with some probability add to A, and with 1 minus that probability, remove from B. Okay, so P add A. And likewise, you can think of remove from B to probability 1 minus PR. So what is that probability? Delta plus divided by delta plus delta minus. Yeah, I'm kind of leaving a question for you. What do you think are the expressions for delta plus and delta minus? Guess the expressions. Any thoughts? I'll try and write down. You can try and complete. So delta plus what would it be? I mean, I'll use f lambda, but you can also, you may not have constraints, in which case lambda is 0. What will be f lambda? In fact, let me be more specific. Delta plus for E conditioned on something, right? Conditioned on delta plus will be looking at what? A or B? A. What do you think this will be? F lambda of A union E. Basically, if you're trying to add E here, what is the gain? Right? Minus F lambda of A. So by similar argument, can you guess what is delta minus? Will be E given. What will that be? Think a little carefully. Yeah. Huh? You're removing from B, not adding to B. Now, it's not necessary that this function is not monotone, by the way, right? So it may happen that after removing an element, you are actually gaining. So you may have to look at absolute value then, or what? One of them is negative. What do you do? If delta plus EA is negative, what would you do? Should you even add? Should you even consider adding? So this is pretty much what you said. I've summarized it here. But my next question to you all is, so what? I mean, this is the answer. Fine. So this, if both of these are positive, that's okay. This you use to calibrate your probability of adding. If one of them is negative, then that action you cannot consider at all, right? And what's the point? Right? Ignore the addition if this is negative. Ignore the deletion if I can't. Here's what I'll like. So ignore the addition if delta plus is negative, and ignore the deletion if delta minus is negative. Yeah, you could try. So you can try more things. So good question. So question is suggestion. Why not do softmax? Exponent some more nice looking probabilistic expression. Why should it be linear like this, right? So good. I mean, you can work on it. There's a lot to be done here, right? Okay, so you can try investigating this. But for whatever reason, this bookbinder in 2012 showed that this bidirectional greedy obtains a half approximation for this unconstrained non-monotone submodular optimization. Maximization. Okay. So half approximation again. Sorry? Yeah. Well, the same element. Your question is, what element are you considering? An element to be added to E. So, no, the greeny and ready must be for the same element. For the same element, what is the what's the gain in adding it to E versus what's the gain in removing it from E? What's the gain in adding it to A and what's the gain in removing it from B? It's the same E. Sorry? What if both are negative? That's a good question. I don't recall exactly what was done, but what I think intuitively you should just ignore that E, right? I mean, if both are negative, then you should just let it remain, basically. Right? There's no gain in removing it from B. There's no gain in adding it to it. Status quo, basically. Okay, so now you can do many other things like greedy for non-monotone submodular functions. For example, you can say, no, I will take non-monotone, but instead of doing this bidirectional search, like there's another alternative. I'll just do greedy. But there's a slight variant you can bring in, which is called the randomized greedy. What does randomization do? There's one additional step here. So you start with empty set for I equals 1 to k. You're choosing now all the potential. This is not monotone, right? So looking at every possible mi, all the elements that give you the best possible next gain, right? So argmax over x. So now what you're looking at is argmax over the subsets of the ground set minus yi, the cardinality x set to k. Right? So such that the summation of v in x, this basically becomes maximus. Right? So you're basically finding the k elements, the next k elements, find all the next k elements whose total gain is max. So like sorting the elements, right? Mounting to sorting the elements. Sorting the elements, the k elements based on gain and picking the top k in mi at this stage, right? What do you do typically in greedy? But now instead of subscribing to that x as mi, you're saying no. From that mi, I'm just going to pick one element randomly. Y as uniformly random element in mi, and only add that yi. Don't add all of them. Now grow your set. Now after adding yi, of course all the other conditional gains would have changed. It's not monotone. Okay, so this is called randomized greedy. Now you're getting a flavor of randomization. Let me. There are many flavors, so we will not get into all of them. Right? We'll show some examples. But here's a comparison of empirical performance of bidirectional greedy. What was bidirectional greedy doing? Growing one set A, shrinking a set B because it's non-monotone. What did randomized greedy do? It's like a beam, right? I create a beam mi at every step, right? It's like a beam. Just a second, sorry. Oh, cardinality constraint, this one, right? Okay, k here, k. We treated the cardinality constraint to be k. So for I equals 1 to 2. Is that okay? Right. So what would you think performs better? Let's just look at this, right? So there are many plots here, but this is a randomized greedy. I think this is in blue color. A randomized greedy, that's this one, right? Not the lightest one, this one, this one. Okay, so I hope you can see. I don't want to mess it up. As against the bidirectional greedy, that's in dark blue. It's not dashed. It's this one. Okay, so bidirectional greedy, I mean, it does comparable, sometimes does better. But it turns out that there are other algorithms which, I mean, simple greedy. I think which is a simple greedy. So this, I think this DLS, it does very good. Yes, just do greedy, normal greedy. Even if it's so, what it's showing is that when we say a function is non-monotone, it's non-monotone only in some regions, right? It's not that you have to discard its monotonicity everywhere. So in practice, you'll find that there are other algorithms like greedy algorithms, simple plain greedy here, which is doing better. The one in red. Is that clear? So greedy algorithms, that's what you're seeing, often perform best in practice without randomization. And theoretically, tightest algorithm. See, for non-monotone, we didn't find any guarantee as such, right? For normal greedy, but yet it's doing well. Okay, so got an idea. Let me know if you have questions. I'm just running through so many variants are there. Now, somebody may say, what about the dispersion function? We talked about dispersion sum and dispersion min, which are not submodular. Okay, these two, dispersion sum and dispersion min, are not submodular, are not even submodular. Forget about monotonicity. Now, what happens to these two, subject to cardinality constraints? So it turns out that the same greedy algorithm achieves a half and 1/4 approximation, not 1 minus 1 over e, but a half and 1/4 approximation for these two functions. The same greedy algorithm. Nothing has changed. Also reassuring. Now we'll look at another very interesting implementation trait. So what was the complexity of greedy? Complexity of greedy we saw is what? Every iteration you are basically looking at n minus n elements, n minus 1 elements, right? N minus k plus 1, something like this, right? Which is basically order of n times k, right? Where the cardinality of V is n. But in practice, this is also a little expensive. Okay? And it turns out that you don't have to do this. I'll give an example. I'll actually run through this little carefully. So there is a very interesting variant, interesting engineering trick without any loss. It's called the lazy greedy trick. The idea is, again, this is, if you've done data structures, you have heard, what are priority queues. Use priority queues and maintain upper bounds on the marginal gains. Okay, so I'm going to use this canonical picture. So let's just for all elements. And let's say I have some upper. Can be assured that for the topmost element, I can't write that in. So I'm going to just say E hat. E hat is the topmost element. So can we assure that for the if for the topmost element E hat, the utility function, not utility, the upper bound function, the let me actually write it. So if f the function conditional gain of f hat given the current. So let's say the current is ai, okay, given ai. If that is greater than equal to the next element in this, right? So this E is the next element in this priority queue. Right? E hat is the topmost element in the priority. So can we assure that if the topmost element E hat, we had f of E hat given ai is greater than equal to u of E, then there is no need to consider the conditional gain of elements below E in the priority queue. This is the question we are going to ask. Okay, so let's say there are a bunch of elements here. Let me use a different color. A whole bunch of elements here. And my question is, if I can ensure this, then there is no need to consider conditional gain of elements below E in the priority queue, all these other elements. I don't have to consider them at all. Then you can see that I don't have to evaluate all the elements. Maintain this priority queue, take the top, find its conditional gain, compare with the next element in the priority queues, U, not, right? And I know that upper bound, U is like an upper bound. So what's the semantics? Semantics of UE is that it is an upper bound on the gain f of E given AI. I didn't even compute f of E given AI. See, I only computed f of E hat given AI, the topmost guy. But I know that upper bound for E given AI itself is not doing better than the conditional gain for E hat. And why should I consider the next element or any of them below? Okay. Is this basic idea clear? What do you mean by it? What is U hat? Okay, that's I'm going to go to the next slide. But if we had this, then you think there'll be some efficiency, right? And the answer is you can get this using submodularity. Okay, the trick is that submodularity gives you this UE. Yes. No. So we have to. Okay, that's a good question. So UE we have to calculate. So there's a little bit more work you need to do. You have to keep updating. When will you update? For example, if UE hat, if I pick E hat, then I'll have to certainly update it for E hat now, right? The topmost element I pick, I have to update its upper bound. Do I have to update for all the elements? You don't have to update all the time because upper bound is being maintained. But in case it happens that the next element UE, right, is greater than E hat AI, then I have to do some more work. So it's basically, I mean, it may not give you guaranteed. Worst case may still be the same, right? But very good chance that for the next element I don't have to. But if this happens, it's a good question. So if this doesn't happen, then you'll have to update. And you'll keep going down, and keep updating for all the ones that you had to kind of proceed with, right? It's a good question. Let's complete this discussion. So I'm going to just copy this for the next slide. Okay, so this is a lazy greedy intuition. I think I'm just repeating this point. Maintains an upper bound E of the marginal gain of every item E and reduces them as the optimal set grows. So that is a point. So what will happen is, in such a case, if E hat given AI will not be less than greater than equal to UE, right? Right. So then you'll have to go down. So so UE was upper bound. We have to revise upper bound of E, right? We might need to revise upper bound of E based on actually computing f of E given AI. Okay, but now let me go to the most curious of it. What is this upper bound? Okay, so just notice this one property very, very carefully. Okay, and this is critical to the upper bound. Submodularity means that the marginal gain of any element on a set will always be less than or equal to that on the smaller set. Smaller subset. I mean, if you want, let's be very specific. Smaller. I should have called it smaller. And we are growing, right? It's not arbitrary set. It's a smaller subset. Should have made it subset. So UE, suppose we make this. UE is the f of E given some previous A. So A stale is a previous A. I call it stale. In some previous, I don't know which A, right? So let's at ith epoch, at ith iteration, this A stale, it would be any of the A stale. Could be any of the AI minus 1, AI minus 2, A0. Any of the previous ones. That's all I'm saying. That's A stale. Okay. So f of E given A stale is f of E given some A small. Basically, A small, the previous guy, right? So let's just call it A stale is the same as A small. So oh, I've said this. I've said this already. I don't have to repeat it. So we are where you have that A stale is the same as A small, which is the same, which is a subset of A large. What is A large? A large is nothing but the current AI. Okay, I'm just giving intuitive names. AI is A large. So f of E stale is equal to f of E small, which is greater than equal to f of E given A large. As I keep adding elements, I don't expect the conditional gain to increase. That's a modularity. So why can't I use a previous E given an A stale to be my upper bound? That's the basic idea. Right? That very intuitive. So the rest is exactly what we discussed on the previous slide. E hat is an element at the top of the priority queue. In any iteration, by maintaining upper bounds in a descending order, avoid scanning the entire remaining ground set to look for the next best element to add. So that is if E of A hat given A current, that is AI. I'm just giving intuitive names. AI is greater than equal to U of E. And E is the next best element. So I'm just let me just reproduce this. Okay, this is the picture. Right? So if this is the case, then there is no need to scan the other elements, right? No elements below E in the priority. These you don't have to scan. Because you have found this UE be a good proxy to what best you could have done using U hat. And this is basically, I can update my UE hat. This will be my new UE hat. Okay, I hope this is clear. So it makes the optimizer very fast in practice while yielding the same exact result. There's no change in the result. We are not approximating FE of A. FE had given A current that we have to compute the top of the game. But we are saying we are comparing it with an upper bound on the margin conditional gains on other elements in the list. So that's the upper bound is used as a proxy. If you're better than the upper bound, you're obviously better than the original function. Is this clear? Original function based conditional gain. Okay, so let's just look at this quickly, right? So naive greedy is this one. Okay, but lazy greedy, you can see the green one, right? And certainly it has brought a lot of value. Almost like super very sublinear growth with the number of elements. So complexity is still O and Fk. F is a function evaluation cost. Okay? Nk still order Nk in the worst case. But in practice, as I said, it's much better. I mean, in fact, as I said, it brings this complexity to linear and linear term. Linear in the sense it's like flat. The growth is not. Okay, so there are many variants now. You can make it even faster. But now this making it further faster is at a price. So this is stochastic greedy, and I should bring out not equivalent to the original greedy. Which implies some approximation is happening. It's not the exact the same. Okay, and what is it doing? It's saying, okay, I'm not going to take all my elements. You remember, we took that mi, the next top k elements. So think of instead of doing a top k elements, I'm just going to be even more naive and say I'm going to randomly pick this set of size n by k into log 1 by epsilon. There's a reason why. Oh, it's not come here. Okay, there is a reason why there is an epsilon here. It reflects on the approximation factor. Okay? So let's say I have some epsilon trade-off. I want to relaxation or slackness. So just randomly pick a set T of a particular site. Okay? This T is a subset of the entire ground set. And now instead of finding the best element using your priority queue or whatever, use the priority queue to find the best element in T only. Then add it. So you're adding only from that T and keep growing. Okay, it's a simple stochastic greedy. Now you can add stochastic greedy or lazy also. Stochastic plus lazy. It's called lazier than lazy, right? Than lazy. That's some funny name. So this is just stochastic without lazy greedy. But you can see that lazy greedy is here using the priority queues, and stochastic greedy has taken less time, less cost. But then there's lazier than lazy greedy also. The inclusion of lazy, this becomes lazier than lazy. Okay. And in practice, it gives, okay, what's the approximation factor? 1 minus 1 over E minus epsilon. So for example, if you take epsilon to be 0, basically you're saying that you take the entire set. Means T equals B, the entire set. Okay. So I think we have got a good flavor. We looked at submodular minimization. We had a very brief look at it, but submodular maximization, we got a good idea of algorithms. Now, you can use some of these ideas to also do difference of submodular. I'll see if I get time in the Thursday. Thursday, I just want to take one extra last class. I hope you're okay with it. Thursday. It's an institute holiday, but I hope we just take. So it'll be a little extra reading. So that's why I pushed that to Thursday. I will not do it today. We also seen submodular optimization under constraints. You can also have under submodular constraints. You have seen submodular cover, the dual problem, right? The homework problem. I just want to, one last point here. You can also do greedy solution on other problems, right? Like K-center. K-center, what is metric K-center? So this metric K-center, unlike facility location, which says, okay, find, FS is summation over all the elements in the ground state of the smaller, closest element or most similar element in my subset. Metric center says, oh, I want to find the most similar element, but I want to kind of look at the minimum of all such minimum most similar elements, right? So it's like trying to reduce the width of the points. Tree width, if you have a tree, right? You know what's a tree width. I'm trying to reduce the width of the points or the spread of the points, overall spread of. So that's the only difference, right? Here you have, but this is not submodular. It's min instead of summation. But even though it's not submodular, it gives you, in the minimization gives you half approximation. Right? So it's greedy algorithm, same greedy algorithm. So all I'm trying to say is there are so many other problems where you find submodularity like properties, but they're not exactly submodular, but you will find similar approximation. I mean, not similar, but you may have slightly weaker approximation guarantees. But in practice, they also work pretty well. Yeah. So now I'm just going to spend some time. I'm going to do some demos now. So there's been a lot of research in these years, right? But as I said, there have been lack of good toolkits and benchmarks. That's what we've been offering. So we have this Decile platform, data efficient learning. I'm going to quickly go over Submodlib, which is something you guys are using anyways. So Submodlib is very easy to use. It has extensive documentation. Even the lazier than lazy, I actually have referred you to the documentation. Very, very well done by his student Vishal. So where that documentation somewhere it's lost. Okay. It's there somewhere here. I'm going to go through some examples. So you can go to the submodlib.read the docs.io. Okay, and it has all these query-driven, privacy-preserving, and all of these variants you'll find. And yeah, these are the class of functions: specific location, disparity min, log determinant, all of these obviously. But in addition, you can do mutual information-based functions, which I spent quite some time on. You can do conditional gain-based functions there, and you can also do conditional gain and mutual information together. Okay. So here's submodlib.read data.io. So some modular functions, okay, you can see this, right? All of these functions are there. Scrolling here is not very. How to make this? Okay. Yeah, conditional gain functions. How to scroll this down? Yeah. Now it is shown up there. Conditional mutual information functions. All of them. There's a lot of the math aspect is also being taken care of, even as you might be interested in the use of these functions, right? With due citations. So I find it very interesting to just navigate through this. Given the background I have, you'll find you'll be able to relate to most of the components here very easily. Also, you'll find optimizers, right? Naive greedy, stochastic random greedy. I talked about lazier than lazy greedy, which is also called accelerated greedy, because it's the same greedy with acceleration. But lazy greedy is a combination of stochastic and lazy greedy. So all of these are implemented. You can profile them as well. Okay. So now let's go back to the slides. As I said, these are also there. Conditional gain, mutual information, combinations of these two are also there. Okay, now one more additional aspect of engineering, which is very important in this library. It's all, by the way, is in C++. But in addition, it also has something called memoization. Okay, so as you keep adding elements for each class of functions, can you reuse some of the computations from the previous iteration, right? So cache intermediate variables to be able to faster compute the gains of adding elements to space, right? So if I'm looking at, say, the gain of adding E to AI, would I? The question is, can it also benefit from computations done for, say, AI minus 1? Okay, this is getting more engineering, but it's very important. This also has important mathematical underpinnings. So it turns that this can be done by use of pre-compute statistics for each set X. So given the pre-computed statistics, the evaluation of the gains is much more efficient. So let's look at this, right? So I have V1, V2, Vj, and I'm trying to add U to it. A new element I'm trying to add. F of U given Sj is what I wanted. Sj is this set. Now, what you do with pre-compute is, I won't just treat it as U given Sj. Instead, I'll say U given Sj, comma Pf Sj, which are some pre-computed statistics. Okay, and I'm going to give you examples of what these pre-computed statistics are. Simplest case, right? Simplest case. If I had to look at, you remember the proof of, or recall the proof of submodularity of facility location. Remember, there was one important step we had there. In the proof, what did we say? We said that if I had max of some element I in V, right, to J in X, but this X itself, let's say, is X union E, right? Sij. I is outside. I is too cramped for space, right? What was this? This is a max of two different maxes. So if I had to compute it, right? So if this is max of two maxes, I don't have space here. Let me write it somewhere else. Okay, so this what was this? It was max of the first term was max over J in X of Sij, comma S IE, something like this, right? So if I'm adding an element, then why can't I preserve this? This is the idea of memoization. Can this be a pre-computed statistic? Can this be my part of what I'm calling as PF? Oh, sorry, I've used Sj in both settings, so I hope you don't get confused. This Sj is similarity, which I'd used earlier. This Sj here is like evolving set. So if you want, I'll put a delta here. Delta. Let this be delta. I hope now it will not be confusing. So think of this as I should just be careful with notation here. So this is like my SJ. Is this clear? So this is my pre-compute statistic that I'm talking about. Can't I just make use of these? So, I mean, it's easy. Once you get the hang, it's easy. You have to now work it out carefully for different kinds of submodular functions. Yeah, so these are pre-compute statistics for each of these. Facility location, I already showed you this, right? Max over K in K of SIK, I in V. That's a pre-compute stat. So this is the column of all the pre-compute stats. Likewise, you can do the pre-compute stat for all the others. So you can try and work it out. I won't spend time. Saturated coverage, graph cut. But what's interesting is the complexity of computation has now gone from order n squared to order n. Order n squared to order n in many cases, right? Sometimes it's, cubic to square. So this has been elaborated. Use a set of concepts. For example, if you're looking at feature-based functions, and some of them are looking at distances. These are looking at distances. These three look at distances. But in the compute stat will be looking different, but the spirit is the same. I'll not spend more time on this. So this has also been implemented, and in practice, if you look at the memoization, then right, so the time rate there's like 212 times speed up. So this is speed up. This is speed up. It's like with memoization. And this is without. I think this should be good enough, right? So you get an idea why it's so important. Okay, so now I'm going to, yeah, this is like the big picture, submodel optimization. Hopefully, next class I like to revisit this big picture. But I think we've seen all of these, many of these variants. But Submodlib specifically, it's very easy to use. Just a few lines of code. Here you can see from Submodlib import facility location function. You create an object facility location, and then you basically what you have done is identified from the set of points, those blue points, which is the set X. This is my set X. Or you can do query driven. So query could be your point here in green. So you say query data. You just need to give the query data and then specify. Okay, the idea is you also can specify the optimizer: naive greedy, lazier than lazy greedy. But obviously you will do accelerated greedy. There's no need of not doing that, unless there are some corner cases where the priority queue is never used. But those are very pathological cases. So mostly you should go for accelerated greedy. And then you can see the greedy list here. Subject to this query, now suddenly you'll find that because you are interested in this query, more points are being drawn closer to the query, right? And it has kind of totally ignored this point blue here, right? Because it's far away from the query. Right? In fact, it has ignored this as well, because it's not relevant to the query. But the moment you put a privacy preserving constraint right here, private data, single query data, this is this one, P, suddenly it has repelled all the points. You'll find that no points in this cluster, and points which were not being picked up, case of query focus, are not being picked. It's very easy to use. Lazy greedy, accelerated greedy, the worst case is the same complexity as. So for that worst case, the priority queue will become a headache. because you keep on updating it for no good avail. There'll be a constant factor in the worst case, but practically that doesn't happen. Okay, so let's just run through some of these. Okay, so this is I think I've given all these links here. So general submodular function, submodular mutual information, submodular conditional gain, and image summarization. Just quickly run through these. So this is the image collection, I think. This is a general submodular functions. So install submodlib using pip. You can create this handcrafted data. I was showing exactly that handcrafted data here, right? Select by facility location. You can choose your function, change it if you want. So these are nice notebooks prepared by Vishal. So yeah, what happens if we do log det? So this is facility location. The first instance was facility location here. But what happens if we do log det? Diversity becomes more important, right? It's actually ended up picking up this outlier. You see that? So it was there even then. I think it just picked some other outlier. This outlier, 8.8. In fact, it prints all the points in the order in which they're selected. So it also prints the order. That may be useful for diagnosis. So it has picked up this point 8. 8 means the 8th point that was picked up. 8 in the order. So the first point it picked up was probably 0 this here, then 1 was here. You can see the order is of DPP, right? 0, 1, then 2, it has gone really corners. Then 3, this corner, then 4, this corner, will come back here, and 5, and 8, it has picked like in an afterthought because it has insisting for diversity. You can do this for set cover. Okay, set cover, you can look at the features. Feature space. What are the concepts being covered? These are the concepts that you're looking at for coverage. So you can do this, yeah. You can do a different representative set and so on. So this is general submodular, and then there is submodular mutual information functions. Again, you can do this for handcrafted data. I'll not spend too much time on this. So this let me go to the other. This conditional gains. So again, the example I was showing earlier of this red point, you can pick multiple privacy points as well. And you can see the kind of selection that happens, or log determinant conditional gain, and so on. So you can please try it out. You can also do combination, which is conditional gain and mutual information. So you can, I didn't show that in that slide, but you can have a red and a green point both. And then you can really, it's interesting to observe what happens, right? So look at the sequence of points on which it picks. So it has picked up 1, drawn to 1 to this green point. But then 2, it has got really far away because it's trying to now, I think this must be log det. Oh, facility, FL, facility location. Yeah. And then 2 has gone far away. I think 2 is also trying to cover for these set of points. Oh, by the way, a lot depends on the similarity value, right? So what is the Sij that you design? In fact, if you're doing deep machine learning, the Sijs could be based on gradient similarities at some intermediate step of your learning. And yeah, all of these. One very interesting thing is this real world application of images. So please try this out. This is very interesting. You have an image collection that you have loaded here, the image collection. And then you can do query focused. Okay, so these are the images, and I think the queries is taken as a dog in the church. So what happens if you take the dog in church? You can, first of all, you can do Disney visualization. Where is it gone? I think the Disney visualization is probably disabled here. And then you can look at what get picked up, right? So lots of dogs if you're doing facility location. Facility location will be biased by the most popular guy. So there may be too many dogs and very few churches. And it is not cared for diversity per se, right? Because it's trying to represent. But if you look at log det, this is a T-SNE. You can look at T-SNE, like where it has picked the T-SNE plot. Right. So the query was here. this one, and in response, it has basically picked up the summary, which is all here, and there's one point here. One church, I think it has got. Oh, there are two. Sorry, there's one query here and one query here. I forgot. There are two query points, right? There is found lots of dogs and one church. I don't know why it's picked only one church. I have to investigate that. Right, and then yeah, you can do this for others. But if you look at log.mi, you'll find that it just tries to diversify significantly. You'll find some other objects also coming up, just because it wants diversity. So try it out. That this will be very interesting. What I'll be doing these are the different demos I had to run you through. The entire application of these specific location, etc., has also been for data augmentation. I just conclude with this. So trust is one use case where you have a large unlabeled data set. You may have a target set, which is your query. This is your query set, right, which we were calling in green. So given the query set, what you're trying to do is maximize your mutual information functions to identify the T, which have the maximum mutual information with the Q. Right? So like say nighttime images. I want only those which are like nighttime images. So then I can take this target set and label them. Instead of labeling randomly, I only label a diverse small representative set. This could also be used for tuning confusion matrices. For example, if I want false negatives to be small, right? False negatives. So I can do the following. I can do I want to increase my true positives, right? So I can do a true positive from a false negative. So my target should have high, mutual information with the true positives and should be dissimilar from the false negatives. So if you're think of iterating on the confusion matrix like this, right? So that the confusion matrix becomes what? Diagonally dominant. That's what we aspire for, right? You would like this to be dominating. So you want to really push all the other elements to this diagram. These are other use cases. I'll talk about two more use cases in the next class from a purely machine learning perspective only. Thanks. We'll meet on Thursday, I hope, at the same time.